Today on Interview 360, the first ever mission to deflect an asteroid, moving an asteroid out of its current path, changing its orbit, and therefore changing its ultimate destination. And that's the point of the mission, finding a way to defend our planet if an asteroid, some type of a cosmic body, were traveling on a collision course with Earth. Dr. Elena Adams is here. She is the technical lead for this mission. Elena, good to see you.
Nice to see you too.
Sometimes this sounds like the plot for a movie, but this is serious business.
Oh, absolutely. Planetary defense is very serious business. There are many cosmic bodies around us that could impact Earth, especially asteroids that are, called near-Earth asteroids or near-Earth objects, because sometimes comets come by pretty close as well. And we're here to protect you against those. Right,
and they've been identified. There have been thousands of objects identified as potentially hazardous.
Absolutely, and they're being identified all the time, from a lot of the ground assets. A lot of the telescopes on Earth are dedicated to spending time to look around and map trajectories of these objects.
I mean, this is an international issue. No matter where you are in the world, this is important to you.
Mm-hmm. Absolutely, yeah. So it's not just one country, right? It's really a global problem. So, for example, for DART, for our mission, it is a large number of institutes and institutions that are coming together to do this.
There's always an acronym. Can't be a space mission without an acronym, right? So DART, Double Asteroid
Redirect Test.
Okay.
Yeah. So. It is kind of cute because we're literally hitting an asteroid, but it's also kind of like a dart, and it has to be a dart because it's so far away.
How big is the object that you're actually going to crash into?
So it's about the size of the Washington Monument.
This is a cosmic body going very fast.
Yeah, it's going something close to 76,000 miles per hour. So we are basically getting ourselves in the way of this object and slamming into its moon.
And so you're going to crash into it at a particular speed as well.
Yeah, so I guess a good example would be about 2 minutes out from the asteroid would be us, it's 6 kilometers per second, but that means that, traveling from Boston to DC in 2 minutes. So, and imagine that your telescope on the spacecraft has to be able to see like the size of the Washington Monument from it.
So essentially you're taking a spacecraft about the size of a refrigerator?
Yeah, a large refrigerator.
A large refrigerator.
Yeah.
And you're just ramming it into an asteroid.
That's right. It's a pretty simple problem, except for the fact that it's hard to find the asteroid and hard to guide yourself to hit that
And
asteroid.
You only have to adjust its trajectory just a small amount, right?
That's right, just a few minutes. So the two asteroids are tidally locked, which means one is orbiting another one. So it's the orbit of the smaller asteroid is about 12 hours. So we're going to change its orbit by about 8 minutes, and that will be observed from Earth from ground-based telescopes. So it's kind of like finding the needle in a haystack in the first place for the asteroid. We don't actually see the asteroid itself until the main asteroid. So there are two asteroids. One is a larger one, it's called Didymos A, and then there's the small moon which we're trying to hit, which is Didymos B. And we don't see the whole system until about 30 days out, so we don't actually know what we're searching for and trying to hit. We don't see it on our cameras, on our telescope at all until about 30 days out. And we don't see the smaller asteroid at all until about an hour out. So we're guiding towards something that we don't see at all until about an hour out. And
that's exciting and frightening at the same time.
It is, yeah. So we're using this new type of technology called SmartNav, but it's really based on kind of the missile guiding things that APL has developed over many years, and it's literally guiding us into a very small body.
Right, and this Didymos A and Didymos B.
Yeah.
They have been identified as potentially hazardous objects, right? Because they're coming close to Earth.
That's right. The orbit of so Earth sits at 1 astronomical unit from the sun. Didymos system comes as 1.01 close to Earth.
It's close enough.
It's close enough that it could impact Earth if its orbit was changed enough. Yeah.
And I would have thought by now there would have been plans already in place to take care of potential impacts with asteroids or comets, cosmic bodies?
Yeah, there definitely are.
So there are plans.
There are many plans, but this is the first test of these plans. So while everything is great on paper, but then
have
when
to
you
know if it
actually,
works.
yeah, you have to know that A, you can build it really fast, and then B, that you can actually launch it fast enough, because it takes a long time to develop a NASA mission. Most missions take like 10 years to develop. And in our case, we're building it in 4, and we're going to launch it and hit an asteroid in just 15 months. So it's a short turnaround time for us to reach the asteroid and hit it too.
There's a lot of new technology that you guys are breaking in on.
That's right. This is not a science mission. This is a technology demonstration mission, and our primary goal is to move an asteroid. But also, in addition to that, we're demonstrating many other technologies for NASA that are going to allow NASA to go to new places much easier in the future.
There's a lot of firsts in this.
Yes, there are. We're the first mission to fly the Next Sea ion thruster, which is a revolutionary propulsion technology that has been developed in NASA for the last 10 years. It is basically using ions to propel us through space. It's going to allow us to go to planets and really change our course. Mission design in space is very hard, and it will allow us to change the course of our trajectory very easy. The other piece that we're flying that's kind of new is our new communication system as well, because if you think about it, we're trying to hit the asteroid, and we're trying to get the last image to the ground at the same time, because once we hit, there's no images coming back. So our whole mission is trying to take pictures as we're getting closer and closer and closer to the asteroid. So in the last 2.5 seconds, we're going to be sending images back. So we're testing out a new communication system as well the whole time while we're imaging the asteroid and we're sending images back. Our high-gain antenna has to be pointed at Earth, communicating through the deep space network down to the ground.
Right, because
Yeah.
once you have an impact with this
Yes,
asteroid,
I think
the ship
that-
no longer exists.
No,
right?
the ship no longer exists. In addition, the Europeans might be supplying us a small spacecraft called CubeSat and LiCube, which will actually take pictures of us, kind of like a selfie of DART as it hits the asteroid, and imaging the ejecta, the plume that it's going to come out. So that's really exciting.
A satellite selfie.
Yeah, a satellite selfie, because you need one of those. I mean, it's kind of hard to.
That's novel.
Yeah.
You'll see that in an iPhone commercial coming
Yes.
up. How big of a plume?
So it's going to be.
Do we know?
We don't really
Yeah.
know very well. I mean, there are different models that show how big the plume is going to be, but it's not going to be visible from the ground because we can't even see the asteroid from the ground.
Right.
But and so that's why LiCube is going to be there to try to image it.
I love the tagline for this mission. The tagline is, asteroids have been hitting the Earth for billions of years. In 2022, we hit back.
Yeah.
It's very movie.
It is very movie, just like in the Armageddon.
Right. Okay. I mean, we can go in. There are lots of movies with the plot of an asteroid hitting the Earth.
That's right.
The difference in this, of course, you don't have Bruce Willis,
Yes.
and you're not setting off a nuclear device on the asteroid.
That's right. Usually you would use a nuclear device for a larger type of asteroid. We're okay with the size we're at. Because the Planetary Defense Office develops all these strategies on what kind of size of asteroid, what kind of mitigation technique you would use. So for nuclear, you need actually to hit a much larger asteroid. And then there's also gravity tractor techniques where you get really close to the asteroid and kind of guide it out of the way by basically being next to it by gravity. And that's used for smaller asteroids. But we're kind of in the middle with the right size for Didymos B.
Do you watch movies about asteroids hitting the Earth as a plot? Because there are so many of them, like Armageddon. Do you
Yeah.
watch those and judge their scientific
I definitely judge.
basis?
I do enjoy a good science fiction movie because of that. Mainly because I was an atmospheric scientist before. I enjoy Twister the best, and The Core is one of my favorites as well, just where they tunnel all the way into the core of the Earth.
That's a
But
really good movie.
It is a very good
I really enjoyed that.
Yes, and scientifically not correct at all.
Of course not,
But
no.
that's what makes it so much
It
fun.
rarely is, because we didn't joke about Armageddon, the movie,
Yeah.
where they ran into the asteroid or blasted the asteroid, basically.
right, yeah.
Scientifically, that didn't really add up either, did it?
No, it didn't really, and I think sending the humans to an asteroid is not the most efficient way of doing it. Sending a robotic spacecraft seems more appropriate.
And you don't also want to hit this asteroid too hard because you don't want to break it into fragments, right?
That's
or you don't
right.
want to have other smaller fragments raining down.
Absolutely, and that's what a nuclear blast would do for some of these different sizes of asteroids. And also, it all depends on the type of asteroid it is too. Some of the asteroids are made out of rock. Some of the asteroids are more, have more metals in them. Other asteroids or comets, for example, comets are mostly water. So the type of mitigation approach for each one of these is very different. Asteroids come to Earth all the time. They come in small sizes like meteorites, or they come in larger sizes. So the the dinosaur killer, 65 million years ago, that was a 10-kilometer asteroid that hit. But those don't come very often. Much more often are these Tunguska-sized ones, which happen on a 100 to a few hundred-year scale. And that was in 1908 was
that
the
was
last
in Russia
one.
also,
Yeah, that was
right?
in Russia. Yeah. So that's the one that the blast was so large that it was about 200 times the amount of
the atomic bomb in
right.
Hiroshima.
Yeah, in Hiroshima.
Right.
So that was really big. And so then the latest big one is the 2013 one, which was much smaller, the Chelyabinsk event, which,
Right.
while did not kill anybody, it still damaged a lot of property.
Right.
But the other thing that really is important for DART is that we're a very low-cost mission. So this is not billions of dollars being spent on trying to make this work. This is a fairly low-cost mission for NASA to just go and demonstrate this.
You still have a lot of work still yet to do on this, right? There's lots of deadlines.
So we're launching in the middle of 2021, so in June 2021, so that's a 15-month cruise. But before that happens, we need to procure our rocket. We need to be able to finish the final design of our spacecraft. We need to build our instrument, Draco. That's the camera that's watching the asteroid. So there's a lot of work to do. So we're going to be in our critical design phase at this point.
Wow.
Yeah, there's a lot to do.
Yeah, and everyone on the planet appreciates what you're doing, and we're depending on you.
Thank
this
you.
is serious business.
Absolutely.
Yeah. And thank you for being here.
Thank you for having me.
And we appreciate you watching. See you back here next time. This is Interview 360.